So I'll give you 3 classes. The first 2 will be about transport, meaning essentially problems that are related to generative modeling, where you are given data from a probability density function or a distribution, and you'd like to generate more data or understand something about this distribution. About Markov chain Monte Carlo, meaning sampling a distribution that you know only up to a normalization factor. That's going to be the 2 first lectures. And then the third one will be on the infinite with limits / mean field regime, but I'll try to position that more into discussing what could be called the benefit of over-parameterization, and I'll try to make that clear. Okay? So for the first 2 lectures, the setup will be like this. You imagine that you have a probability density function, and I'll motivate what I'm doing here in a minute. I'll denote it like, rho star of x. I'll take x to be in some omega, which will either be RD, I'll follow the D of Julia, or the torus. And this is going to be this probability density function for simplicity will be such that for all x in omega, this guy I'll assume is strictly positive and is going to be normalized. Like that. Okay? And then what we want to do, I'll tell you in a minute that we can generalize all this, but what we're going to do is that there's 2 classes of problem that we're going to be looking at. One is that there's data from rho star available. But no other info. You just have a whole bunch of data, and you'd like to learn something about this distribution or generate more data from the distribution, okay, from the density. Okay? So this is something which is more in the generative, it's a generative model type of problem. And this class of problem, what I'm going to discuss today, this is what I'm going to mainly discuss today. I will relate that to this recent advance, in particular in score-based diffusion modeling, which are these methods that have been recently introduced and that allow you feed a neural network a whole bunch of pictures, say photographs of a famous actor and actress, and then you build a generative model that can create this deep fake. It can now create new figures, new images, new photographs that look like they are famous actors even though they are completely fake. Okay, so I'll try to explain, in this context how that is done. And then, tomorrow, this in a way is a simpler problem. I'll explain to you why than the one that I'm here. The other one is that rho star x is given to you thus in the form of, say, a Gibbs distribution like this, right? And this guy you don't know, the normalization factor you don't know, and this one you can evaluate pointwise, this potential, and you'd like to generate data. You'd like to have, you'd like to sample it, either, to have samples or to compute expectations. Okay? That's going to be for tomorrow. As I said, I'm going to connect here with the problem that come, important sampling. And Markov chain Monte Carlo. Right? This problem is in a way harder than this one because you have no data. This one, in a way, has some simplifying feature, which is that you assume that you already know something about the distribution, which is that you have the data that's available. Okay? Okay, so in terms of assumption, you can generalize part of what I'm going to discuss in cases where these are more complicated subset of RD. You have a prior distribution that could be singular on that set. So you don't need to work necessarily with densities, but to keep the level of technicality sufficiently low, I'll just discuss, stick to this case. Okay? Okay. Right, so the way we're going to think about this, right, and that's the idea of transport, is that so we're going to, we're going to call this guy the target. right? And we're going to introduce a Bayes distribution, a Bayes PDF. I'll simply denote it rho B of x. It has the same properties, but it's simple. Think Gaussian if you're in RD and 0, 1, for example, or uniform distribution if you're on the torus. Okay? So it's something that you can easily sample from, right? And you know its property. For example, if it's a Gaussian, you know, well, this factor is just a quadratic form, x squared, if it's n0, 1, and you know this guy because there's a partition function in that case that you know. I forgot to say that. Of course, you know, this is, for physicists, this is just a standard Gibbs distribution. This is the partition function. If you do Bayesian inference, you can formulate things in this way too, where this would be like, you know, the likelihood. In that case, you would need to put a prior, okay? But coming back to that, you assume that you have a Bayes PDF and it is simple. And the basic idea of this transport model is essentially what we're going to try to do is to come, so, you know, I'm going to make a little picture here to try to explain, which is that you have this, you know, this is rho B, it's fairly simple, and then somewhere here there is, you know, something which is quite complicated, could be multimodal. This is the rho star, right? And what we're going to try to do, and that's what I want to explain, is to try to find a transformation that pushes this way and, you know, potentially is invertible, so that you can push this density onto rho star and rho star onto B. In other words, we're going to try to, you know, do things which are such that you're going to view rho star as being the push forward by this map of rho B. That's the goal. I'll explain to you what this push forward is. Bear with me for a minute, okay? Now, before we go there,
this means that also we can think of as discovering U star as the norm of the square root of T inverse, or is that?
I will get to that. I'll give you expression for Z star, for U star, for you know, all of that. If you have data, and we'll see that in a minute. Now, what I'm going to be, this is a remark I'll come back on later. I'm discussing here probability density function, but many things that I'm describing here can in fact be generalized fairly easily to a case where this would be a target function, say a classifier, for example, that is quite complicated. And what you'd like to do is to make a transformation of your input space in such a way that you take the data, if you wish, or the classifier, right, and you turn it, it's typically quite complicated, and you turn it into something simple. Like, for example, you could imagine that, you know, you're on the sphere, it's been partitioned into two classes, right, that define, you know, something, in this case, in fact, that could even be a probability density, right, and what you'd like to do is, you know, to build this classifier, and the way you're going to think about it is, in fact, to distort the sphere, move things around on the sphere in such a way that you'll put all the data from one class in the upper hemisphere, north, and all the rest in the south hemisphere, so that the classification becomes very simple. Okay? Now, I need to explain to you how we're going to do this and give a little bit of background here. So the way we're going to do that, and the way we're going to do that is, in fact, by constructing this map sort of iteratively, as something that evolves in time. So we're going to construct a map which is such that at time t equals 0 it's rho B, and at time t equals 1 it's rho star. Okay? And I need to give you a little bit of background on that, so I'm going to start to do that now. So the way we're going to think about this is that I'm going to introduce, so I don't know how many of you are familiar with PDEs, but there'll be a little bit of PDE here and solution by method of characteristics, which in fact you have already seen because there was a class, who gave a class with, Francis gave a class about optimal control. This actually is some of the things I'm talking about smell a little bit like optimal control. So there was a formula for the Hamilton-Jacobi equation. You can prove it the way I'll do now, in a much simpler case, in fact. Okay, so the way we're going to think about this is that we're going to introduce an evolution equation, a dt rho t, which will simply be a transport equation with a velocity field Okay, like that. Okay, so everything depends on x. At some point, I'll drop these things. So I'm going to look at this equation, right? And then, so we're going to impose that at time t equals 0, let's forget about that, this is rho b, and at time t equals 1, this is rho star. I think about that this way. Okay. So now, and the aim here will be to try to find a velocity field that achieves this. Okay? And so, now I need to, why is this picture useful? I need to explain. Well, on the one hand, because I'll show you that there is existence result for velocity field like that, right? That guarantee that you can actually, there's a solution to this problem, in particular under the condition that they have given here, that the density are everywhere positive, okay? And then, more importantly, I'll show you that there is a Lagrangian formulation of this equation, which allows you to solve it by the method of characteristics, which will allow you at the end to push samples forward and backward, okay, to achieve this here. Okay, so let's proceed by steps. So the first statement, okay, so there is two, for the moment, let's forget about this problem, and let's forget about this for a minute. Yeah, of course.
Is it guaranteed this preserves the weight of the distribution? Like that it still integrates to 1?
Yes, it does. That precisely, yes. I'll get back to that. In fact, if you don't want to work, this is balanced transport. If you want to work, if this was, something like a classifier, or you're interested in regression, we will have to do something a little bit different, and I can actually write it already, why not? You would then do something which is unbalanced transport, which is that you'd replace this 0, say, for example, by a btx times rho t. Okay, and then you'd have to learn the v and the b. That would be unbalanced transport. But for the moment, we're going to simply put that to 0 because I don't need that that's the simplification fact that I'm doing today, is that we don't need this term if we are just moving densities. Okay? Okay, so the first thing that I want to, and this is, the first thing I want to look at is that this equation can be solved by the method of characteristics, which means that if you give an initial value problem, you specify this density at some time, then there's a formula that tells you how to express the solution at any other time, forward and backward. For this to be true, you need V here to satisfy certain conditions, so you can imagine that it's Lipschitz in both time and space, and it's bounded, okay? Let me explain to you in a minute why. So there is a if and only if statement that says that if you look at the solution of this equation with some condition, which is that at t equal s, well, let's, I think it's a bit ambiguous, but you'll allow me, it's equal to rho s, right? Then you can express, there's a formula that says the following. It says that if you introduce this equation, make a little picture in a minute. Okay, it's a bit. So you introduce what is called, so at SS, this is equal. So that's the flow map associated with the velocity field, and it's only one t. There's the flow map associated with this velocity field. If you introduce this object, then what you have is that rho of t is the push forward of rho s. And what does that mean? It means that if you take any test function and you integrate f of x with respect to rho t of x, you want to calculate this expectation, the expectation of this f. This guy is identically equal to, so you have this identity, this is what I've written here as right, so what does this say? The push forward means what? It means that if I want to compute the expectation of this function with respect to rho t, and rho t satisfy this equation, what I can do is that I can solve this flow map here, and instead take the expectation with respect to rho s, but not of f at x, f at the flow a little bit, along the line. In other words, you can think about that there's the third way. So this statement is equivalent to this one, is also equivalent to this. It says that if x is drawn from rho s, then, in fact it goes both ways, x s t of x is a sample from rho t. Okay? And we're going to use this property because it will allow us, if we have constructed a map that that does this, right, we'll be able, for example, to take s equals 0, t equal 1, and then rho s would be rho b, and we'll force rho t to be rho star. And then we'll be able to move samples from one to the other. Okay? Let me get to that in a minute. So maybe I can make a little picture here. I'll do it here because I'll prove to you this little statement there. So what you need to imagine is that, these are, these are the flow lines of this velocity field, the Vt there. It's a snapshot. The picture I'm doing here would be really only strictly true if V were not depending on time, it were frozen, right? But what you have is that if this is x, right, then this guy is the xss of x, and then you can propagate it in forward in time toward xt of x, which would be that point, by solving the ODE that's there, and potentially you could go backward by taking t less than s. Is that clear? Is everyone sort of familiar with this this idea? Okay. So
just to make sure, so when you write this differential equation for x, this is differentiation with respect to x.
T. Ooh. This is a flow. So okay, so if it is an ODE, okay, if you try to forget about the x for a minute, right, is really an initial value ODE that's written in a way which is standard when you write flows, which is just that it tells you there's two time. The first one reminds you where the initial condition is taken, and the second one is where you evaluate it. Okay? And so this guy, right, is that there's this velocity field. So this picture would be for V that do not depend on time, right? Is that if you pick an initial condition X, right, the solution of the ODE, right, so the initial condition at S, the solution of the ODE will go forward towards another point, and that's the way you can go like that, okay? And you can do that, this define a flow map, right, in the sense that you can do that for every X, and it's kind of moving all of your points, right? It's a change of frame, if you wish.
So you need a space X to be continuous, so you could basically...
Yes, you need a space to be continuous. X here is really continuous. You need, this doesn't work on graphs, okay, or on network. The space is continuous. It's just a deformation of space, right? And so what you have here is that you have a partial differential equation, and if you wish, this is an Eulerian picture. And here you have an ODE, but it's really an ODE for every initial condition. And so that's the Lagrangian picture. And this is telling you that you can go back and forth between the two. Okay? And it's useful to think about this guy because many statements are easy at that level conceptually, in particular to prove that transport exists. But in practice, it's much easier to use this statement because that's what allows you, in particular, to do the optimization. Okay? Right, so this is for an initial value problem. I still need to go back to that problem, but let me first show you that this is true.
Can I ask those? So
yeah.
To actually solve the Lagrangian version, we need to already know V of t.
That's right.
Right, so you kind of have to start in the Eulerian one. It's not just an existence result, you have to have some estimate for it.
Bear with me. We're going to learn V.
Yeah.
The aim is to learn V. Okay. So bear with me, okay? I'm just giving you a little bit of background material. I'll try to do that sufficiently quickly so that we can go through. Okay, so let me just prove this. Is that, what you do to show that is that let's imagine that I take rho t and I evaluate it at xst of x. And then you take the total derivative with respect to time of this. Okay? So what you end up having just by using chain rule is that, well, first there's the derivative with respect to that. Every argument will be at that point, no? And then what you end up having here is that the dot means with respect to t. Okay, this shorthand for that, I think physicists will, this is the same as that, right? So you have xst times the gradient of this rho t. And I'm not going to write the argument, but all the arguments are always at the same place, okay? Then here you use the equation, you say this guy satisfies vt of x of his tx, right? And then if rho satisfies this equation, you see that you have half of the term coming from there that are there, but there's one that's missing, which is just minus the divergence of Vt evaluated at xst. Let me write it again, and x rho t xst. Now the divergence is only acting on this term. Okay? And because you have that, now you can solve the equation by integrating it from s to t. Right? And that means that you have that rho t of xst of x, so just integrate, is equal to rho s of xss of x, but this is x. And this is just using Duhamel principle.
So how is the divergence only on the v and not on the rho?
Because there were two terms. I just wrote, here there was the divergence of the v, right? If you just use product rule here, there's a divergence of v times rho, right? And then you have v times the gradient of rho. And the v times the gradient of rho is that term, so I'm just missing that one, okay? And so what you end up having is that you have, okay, let's write it with a tau, s tau x d tau. Okay. Now, so this is a solution that in fact you can use to evaluate, to solve the equation, because the reason why we introduce this notation with the flow map here is that it satisfies a group property. In other words, you can, write it here. If you take x of, say, tau s of x, and then you evaluate that at st, this is x of tau t of x. It's just moving along this line in one direction, then a little bit in the other one, right? So this group property here means, in fact, so this is the property of group property of the flow, and this group property allow you, in principle, you could invert that. If you know, if you want to know rho of t at position x, you can invert the flow to know where you need to evaluate the initial condition to give you the value of that solution at that point, and you have this guy here that you need to account for. Okay? Now let me interpret this guy here for you to finally arrive at the formula which is there, which is this guy here is in fact 1 over the Jacobian of the flow. What is the Jacobian of the flow? The j of st of x is simply the determinant of the dxstx, so this matrix, where you see how the flow varies if you vary the initial condition. So that's a matrix. Its determinant defines the Jacobian. Okay? And I claim that this is 1 over the Jacobian simply because if you take d over dt of this guy, right? You can use Fourier's formula that tells you that this is the time derivative of that, is the trace of this times g. J is a scalar. But this guy here is just V by definition, right? This guy is V. This is the matrix that you obtain by taking the gradient of V with respect to its argument. And so this guy here is just the divergence. And if you integrate this equation, you see that the solution is the experiment with the initial condition that J at S of X is equal to X, is equal to 1, sorry. What you end up having is that the solution tells you that you can re-express that simply as being the Jacobian. So I'll write it at the top, this equation, because I will need it. Am I going too fast? No?
Yeah, but what is 1 over the Jacobian?
The whole exponential here. Okay, I'll rewrite it. I'll write what I've obtained here. I'll rewrite in a slightly different way, which is you have that rho t of x st x times the exponent. I'll keep this formula. So I'm just going to solve it. So I'll rewrite it like that. This guy is equal to rho s of x. And this factor here is just the Jacobian. Is the Jacobian of the transformation by the argument that is written there. Okay? And once you have obtained that, you see that, well, essentially you can derive this equation, because if you take the left and the right hand side of this equation and you integrate, you multiply them, so take the right hand side and the left hand side, multiply them by x of stx. You multiply that and integrate over x, both the left and the right hand side. The right hand side is already this. And the left hand side, you can change integration variable and take this guy to be the new integration variable, right? And, well, that's the same. And this is the Jacobian of this transformation, so you get that. Okay? And so you're done. So we'll keep these formulas for a minute. Can I erase that? So we have, this is what we have obtained so far, right? Is that you can do, you can go from Eulerian to Lagrangian, right? Just by, this is the box that we're there. This is just the explanation of that box, these two lines, right? And, equivalently, can be re-expressed like that. And we'll use this. Okay? So this so far tells you that you can solve the problem as, if I want to solve the problem as an initial value problem, right? What I can do is that I can think about solving for the PDE, which is just moving the density, or I can just move points. What we're going to do at the end is just moving samples one by one. So this is the Lagrangian picture. Okay? Maybe for those of you who are not used to PDEs, right? Typically when you solve a PDE, you cannot solve the PDE locally. It's something that is, the PDE is an equation for a function that is a function of x here, t and x. And so typically, if you want to know what this function is, you need to make a global operation over, the whole space. That can be quite complicated. This is telling you that you can probe this solution at specific points if you go along the flow, right? Because it tells you, well, if I know rho of t, okay, if I want to know this guy, for example, right, at that point, well, I can simply calculate this, so, think backward to evaluate where this is actually going, and this is relating then this guy to this guy.
So Eric, you think, just trying to get intuition because I'm not used to these things. So the first equation, that's, as far as I can tell, that would have made sense even in the discrete space. That you would be able to maybe deform a probability distribution from one place to another by just modifying the densities of each particular point without interaction between the different points, right?
But this is, I mean, this is really a transport equation. So it's transporting things continuously. So I'm not sure, in the discrete case it's more complicated. You need to involve the edges, you know, but...
Because this VT only, I mean, this equation don't make sense in the discrete space?
You need to give it a specific meaning, right? I mean, because if you were to think about this in a discrete space, then, you know, X would play the role of nodes, and then you would need to introduce transport by having a kind of a network. The V would be something which is on the edges, right, between these nodes. Then you can give it a meaning, right? But you cannot give it, I mean, then you need to have, you know, a discrete space that's structured, which is, it's not just a collection of points, it would have to be a network, okay? But here I'm really in the continuous setup, right?
So here you're, right, and in the continuous, why is there like, so I guess there is a question which is not intuitive to me, why is there like a unique choice of where to move each particular X, and that's some kind of a principle of fixed action? Or?
It's not unique. So for the moment, I'm just telling you that you can move things around, and that you can move things around with the PDE, or you can move things around with the ODE. Maybe I'm spending too much time on this, because at the end of the day, what I've done here is to solve this equation, as Bryce was saying, if I know V. But this is not what I want to do. At the end of the day, I want to think about this as a problem for V, where instead of imposing one, initial condition, I want to have this boundary condition. So let's think about that for a minute, okay? Which is there a V? No. Forget about what I've written there, and let's think about it slightly differently and ask yourself, is there a V that I can pick in this equation, which is such that with this V, if I solve this equation with this initial condition, using the tricks that I have used there, for example, at time t equal 1, what I will see is that the solution that I reach is precisely the target that I want. Okay? And of course, this relates to optimal transport, except I'm going to do something which is not optimal here. I'm just going to show you that indeed you can solve this problem. So let me show you, no, we have that. Let me make one more result, which is background, which is an existence result for V. The existence of a Vt of x, which is such that, well, I'm going to have that rho t equals 0 is rho b, and that the rho t equal 1 is rho star. Okay? So how do you do that? Well, you do something which is called Diraconia, I'm not sure, Moser transport. So I'm going to, let me explain what this is. This will be, it's not practical. It's just an existence result, but I'll show it to you for, it's, right? So it's, if you have done optimal transport, by the way, already, you already know that this is true, right? Because this is all the work of Brenier, etc. In fact, I'm doing optimal transport in a specific and simple case where I can use the original Monge-Ampère formulation and I don't need to go to Kantorovich, right? Because I have maps here since I have densities. But let me explain to you what you can do, just a feel for the existence. Well, I can construct this guy. Rho b, I do 1 minus t plus rho star times t. Clearly, if t is in between 0 and 1, this is a PDF, because it's a convex combination of two PDF, and it satisfies the boundary condition that I want. At time t equals 0 is rho b, at time t equals 1 is rho star. Right? And now I can do two things. Well, the dt of rho t is equal to rho star minus rho b. Yes? And then, well, I can look at what is the other term in the equation. This is vt that I multiply by rho t. So let's just write it, explicitly. It's this. So if I want to find a v, right, I just need to show that there exists a solution which is such that this is equal to 0. Sorry, this. Right, I'm just adding that. Yes? Well, just say this whole thing here, declare it to be the gradient of a phi of t, of x. This guy, this whole thing, I define, and I say I'm going to express it at the grade of phi of x. But if you do that, you see that what you have obtained is that what does phi needs to satisfy? Well, it's just Poisson equation, right? What you have obtained here, can you see if I go this low? In fact, this guy doesn't depend on time. I just need to solve this equation. This potential satisfies then this equation. This equation has a solution that we know with under the condition that are there. So let me finish this and then. This equation has a solution because this is just the potential that is associated to this density of charge that's neutral. Because they both integrate to 1. The right-hand side integrate to 1. So if I know the phi, well, I can take its gradient, divide by this object, which is allowed because I've made this assumption that everything is positive here, and I get a V. And that V will have the property that the associated rho t is precisely this. So I can do my transport. Okay? This is in no way practical. We don't want to go this way. We don't want to solve PDE, but this is telling the following thing. It says, well, there exists, at least it's not unique because I could put, some dielectric constant here, right? So I could get another potential to satisfy exactly the same thing, but different solution. So it simply says, in fact, I only need the divergence of that object to be equal to that, right? But it says there exists velocity field that will do the trick, which is that if I solve the equation with this velocity field, I'm going to go precisely from my base distribution, which is simple, to the target that is complicated in precisely time t equal 1. And if I have at my disposal one of these velocity field, then I can move samples using the trick that's there. Right? Because now I can do this. Let me rewrite it. I can do that. Okay, I'll write it later. You can take this at time t equal 1. Right? So let's look at this one. If this is at s equals 0, this is a sample drawn from rho b. Give me, if I evaluate this at s equals 0, t equal 1, would give me a sample from rho star. Just pushing it forward. Okay? The transport. Right? Coming back to what I said maybe very briefly about we are working with densities here. Right? If you were to think about functions, in general, functions are not normalized to 1 and they don't necessarily need to be positive, so we need to work a little bit harder. But we could generalize this by making the transport unbalanced. Remove this, play with a B. That will change the mass. Okay, that's going to be for another time. We're going to just think about this way.
Can I ask, is this not practical to do because you have to divide by that difference?
Yes, it's not, I mean, it's a strange transport, which is, the optimal transport here, which we're not going to do, right, would be to move this mass continuously towards there so that, on Wasserstein 2, you would get, the least. This is something where, in fact, this guy disappears and is pumped into that one, right? And if you think about what the velocity that, that's doing that would be doing is doing something very weird. It's actually very singular, this velocity, because of the division. So we're not going to do that. Okay? Okay. But
have you required some sort of like boundedness or Lipschitz condition on rho star?
So,
or maybe different.
No, what I'm requiring here is that the V, right? So all of this requires that the solution of this differential equation, this ODE here, or correspondingly of the PDE there, is unique. In principle, here only used from time t equal 1, but under the condition, for example, that you take this guy to be Lipschitz and bounded in both the argument, it would exist for all times, right? Now, the condition that you need on rho b and rho star are actually quite minimal, but let me not discuss these in the most general case, because now I'll tell you what we need to do to actually learn the velocity field, and we'll see what the conditions are in that case. Okay, it may be more practical. Okay, so what's next now? What's next is, okay, so how to learn the V? Because so far I've give you a trick here, but I just told you it's not practical, right? And so, for someone like me coming more from applied mathematics that has kind of a bit of a naive view on what machine learning is, For me, machine learning is actually, the following thing is to say, can I write down a variational principle for V? Right? Can I write down a variational principle for V and one that's practical, meaning that I can evaluate it on samples? In other words, is there a variational formulation for V which is such that the minimizer give me at least a V that has the property that I want, right? And can I write down this variational principle in such a way that I can evaluate in practice, meaning there's an empirical version I can manipulate. Okay, because, okay, so let's go into these two steps. Or maybe I can erase this and go here. So you remember these properties, right? So, okay, so let's so there are obviously many objective functions that one could take, right? And in order to have an objective, so this is where the condition on rho B will be. But I could, for example, and now what I'm going to do is again use this duality between Eulerian and Lagrangian. I'll play with that, okay? And so one objective function that I could take, because it's practical, is the DKL. So let me write something. I'll write, instead of just saying DKL, let's just write it. So I'm now putting myself in the setup which is different from the one of tomorrow, where I assume that I have data from rho star. If I have data from rho star, that means that I'm assuming that I can estimate empirically expectation with respect to rho star. Okay? So this is not really an expectation, but it's one that I will turn into an expectation in a minute. So let's look at this objective function, right? And let's imagine that I'm going to try to minimize this subject to dt rho t plus the gradient of vt rho t is equal to 0 with rho of t equals 0 equal rho b. So, well, you know already that the minimizer of the, provided that everything here makes sense so that it remains finite, which will have to be true, right? Meaning if rho b is absolutely continuous with respect to rho star, and at that level, I'll show you that in a minute, this DKL makes sense. The minimizer of this, right, will be such that rho t equal 1 equal rho star. Because this is, I can minimize this guy by taking rho t equal 1 equal rho star, right? And I know that it's possible to do it with this equation. That's what I just showed you there. Okay? Now, if you look at this, so let me, let me write that here so that I have a bit more space, which is this says rho t equal 1 equal rho star. So this is a priori a valid objective function, except that it's not quite what I want because the DKL is not an expectation. This is rho star. But then you realize that I can always, look at this. I can expand the log. And all these integrals are over omega. In terms of the minimization, so the minimization here is over V. We'll get to that in a minute, right? What I'm trying to find is a V. So let's write it simply like that. And as at some point we'll have to put that in the right function space for it to make sense, right? Forget about that for a minute. For the moment, this is when we do empirical data. For the moment, I just want to minimize this over V over sufficiently big class, which is guaranteed that they have a solution. So, for example, that contain the solution of the Poisson equation there. Now, if I expand this is a constant. So I can just drop it and focus on the log likelihood, which is here. Right? Yes? Okay. But now there is something that I can do, which is that I can try to move things around in this expression, right? In such a way that, so I'm going to use this, but now I'm going to, pass with the formulation which is so I don't want to use the PDE. I want to go into using my flow map over here. Okay? So is there a way, the next question is there a way to actually, rewrite these things in such a way that what I have is expressed at the level of the flow map? Well, you can, so what shall we do here, right, is, actually, did I do that the right way? Sorry, hold on. Maybe it's a slightly different. No, it's the one I want, I think. You can do it in different, you can do it in different ways. Right, okay, so I'm going to redo simply the calculation that I did. I'll redo so that you see it one more time, maybe in a way which is slightly simpler, which is, suppose that I introduce this guy. I'll just write it with a little bar and only one time because it's probably simpler if we think about it this way. Let's look at this equation and we're going to solve it. They all depend on x. They are flows, each time flows. And I want to solve this with the final condition that this is equal to. So this guy in a way will be the one where I will keep that fixed and vary the other guy. Okay, anyway, let's just write down this equation. Okay? The bar stands for the inverse, so to distinguish it from the x, if you wish. I could remove the bar if you want. It's going to be I'm moving in the other direction. I'm keeping t fixed and s varies. This guy, the reason why I write it like that is because in the note I have denoted that as a short end and this like that. Okay? It doesn't.
If we wanted to drop the bar, we could write just xt1.
Yeah, but take the derivative with respect to the first argument. So it's, the definition is self-contained. This is what it does, right? And they have the v which is like that, right? Then, I can ask myself what is transported by this quantity, right? And this is, well, maybe I need to make sure I'm writing.
Sorry, Rick, maybe I'm just being stupid, but why, like the derivative in that equation is with respect to the second slot, let's say, so why?
Here I want to, I'll do it the other way, but it will be, okay? So, I want to go in the other direction, exactly. So let's suppose that I have this equation here, right? I can redo the little calculation, so let me do it here, maybe. I can redo the little calculation that we have done so that, just as an exercise, at some point I'll just postulate these things so that we don't need to do so much work with it. But, so again, I want to go, I want to use this to solve that, right? And so what we're going to simply do is that we're going to, along the solution of this equation, we'll do this. You look at this guy. What is this? Well, okay, so this guy is equal to the dt of rho t. I'm redoing you have not done this calculation, so we have done it once, but let's do it, right? It's equal to this. But then this is equal to minus the divergence with respect to v of this x bar t. Everything is at x here, times the rho t, right? And now you integrate it from 0 to 1, and you notice that t equal 1 of x bar at t equal 1 of x is equal to the rho at t equals 0 of x bar t equals 0 of x, right, times the divergence. This is really just the Jacobian. So, I could, okay, we've written that. But since I solved this with this final condition, this is rho of t equal 1. So that's x. Okay? And now you see, it's written just above, right? This factor here, okay, I can rewrite, let me rewrite it, as being the integral of, I just substitute, so it's minus the log of rho at time t equals 0 of x bar at time t equals 0 of x plus, I have already one minus there, right? Wait, no, this, okay, I'll find the sign in a minute. Can I erase that formula to give myself a little bit of space? Sorry, bad gestion of the board. And there's this guy, and I need to find the sign. This is t equal 1 now, right? And I can put just as well this to be t since there is no. And so this is the divergence of v of t of x bar of x dt. So we have that. And let me see if I made a mistake. Right, I can write this. I know what's the sign. So when I take the log, I get a minus. Let me just take it. There's a minus here, right? And then, so this is minus the log, which is this one. And then this one is with a plus. Okay? Right? But I forgot to use this condition. So in fact, this is rho b. Right? This is x, but this is rho b. Okay? And so now, what do I have? Is that, well, I can change the problem, which is that I can ask, I can instead of minimizing this over v subject to that, I can minimize this subject to this. Let's write it down. Okay, so let's make an assumption about rho b. Let's imagine that rho b of x is a zb minus 1. I can express it like that. It's easier to think. This ub, if you were in the torus and your uniform ub is just a constant, it's 0, you don't care. But otherwise, think about the Gaussian. So when I take the log of this, right, I get the log of the partition function, which is another constant because there is nothing that depends on v in it, so you can forget about it. And the only thing that remains is the ub. So writing it down, right, instead of doing the problem that's above there, let me erase this guy, right? The problem that was there, I can equivalently do the following thing. Let me write it. I'll try to write it here. And as we go along, you can minimize, still minimize over v, the ub of x bar at time t equals 0 of x plus the integral from 0 to 1 of the divergence of vt of x bar t of x. It's a mess, but I'll make it. Right? I have used the formulation that is there, where now you do this subject to okay? And now in principle, you're in business because you see that I have an objective function, right, that I can in principle evaluate on the data that I have, right, and then I need to do the optimization over v with a constraint. Right. Let me, I don't know if I'm, so the rho b, is it clear? Let me write the rho b here. Rho b is a zb minus 1e to the minus ub. That's what, went from there to there. Okay? So let's discuss now. I think I will not need that anymore. Let's discuss how to do this in practice for a minute. Right? So first of all, what you need to do here. So what I'm going to describe, by the way, for people, I have not given many references so far. It's just to go quick. The reference will be in the note. But this is something that you can do with the framework of neural ODE, which at the end of the day is just what people in optimization had designed before. It's called solving this by method of adjoint. Okay, so let me try to explain how you do that. If I want to do this optimization problem, instead of putting this constraint here, right, you can take an extended Lagrangian. So I'm going to write, you can extend it by adding a term which is like that. This theta t here will be the extended Lagrangian. So there will be two integral. So we're going to integrate that over time. Then we're going to take a rho star of x dx. Let's imagine that. So doing, this guy here is a Lagrange multiplier, right? And doing the optimization with this constraint can be enforced by essentially finding the Lagrange multiplier that satisfies the constraint. Okay? And if you want to, so now if you want to do the optimization in practice, you see that if you take the functional derivative of this object with respect to d over d theta, you get this equation. So if I do d over d theta, this guy, right, of the extended objective which is here, you get that equation. If you do d over the x bar of t, right, you get what's called the Adjoin Equation. And so let's think about what the Adjoin Equation is. Well, when you do over d over dx bar, you will have to integrate that by part. So you're going to get this minus theta dot of x minus this guy is the transpose. This is a matrix now. There is no dot here. This is this matrix. This is the Adjoin Equation, theta x, right, is equal to 0. Except that when you do, the variation with respect, it's not equal to 0. There's one more term, which is the one that is coming from here, right, which is plus this is equal to 0. This is if I take the variation of this extended objective with respect to x. Okay?
Sorry, why with respect to x? Because we are minimizing all v.
That's right, but when you use Lagrange multiplier, the trick of the Lagrange multiplier is that you're introducing a Lagrange multiplier so that you can take x variation with respect to x and v separately, and the Lagrange multiplier is what guarantees that they will match the way you want them to match. Let me finish this, and then I'll try to explain that. And so when you do the integration by parts here, there was a boundary term at 0 that arises, and this boundary term tells you that there's I'm happy. I don't want to spend an enormous amount of time discussing this because it's fairly standard, but I'm happy after the class to go over this, more carefully. So in order to solve this, right, the one that was in white, which is this constraint minimization problem, what you do is that you introduce, so you were going to use what's an adjoint method, which is we enforce this constraint with a Lagrange multiplier, which is that at that level now you have sort of decoupled x and v when you do variation, but you'll use the Lagrange multiplier to guarantee that this is actually true.
But that I understand. I think
Okay.
where I'm lost is I thought that x bar is something fixed in that problem. But
No, so think about how you would do it. You could also do the following thing, which is maybe simpler if you wish. You could think about taking variation of this problem with respect to v, which is what you want to do since you want to minimize over v. But if you do that, and you don't use this adjoint method, then you would have to figure out, if I vary v, I vary x. So if you take the derivative of this objective function with respect to v, there's a hidden derivative that is the derivative of x with respect to v that you can calculate. Okay, that if you do it involve another Jacobian, which is complicated because it increases the size of the system that you need to solve. And so what one does in practice is that we do an adjoint method, which is using a Lagrange multiplier and then what you solve is that you solve this equation as a final value problem. You solve this one as an initial value problem. And then the gradient that you are using at the end is you need not to take the explicit gradient with respect to v of that equation. Does that make sense?
So can I just ask a general question about the problem either in white or in pink?
Mm-hmm.
How much degeneracy is there over the v's?
I'll get to that in a minute. Okay? Bear with me. I am not doing so great with time, but okay. So you can, you can solve this problem this way. So let me, what would you do in practice? Mm-hmm.
To solve the adjoint, you need v.
Yes, but so the way, okay, let me write for you maybe an algorithm, which,
I thought you're looking for some v that would be the minimization. That's what you're doing.
yes.
And
So
x bar is
okay. Let me try to explain this maybe in a more practical way then, which is what you would do in practice. Okay. So first of all, just to simplify, now this is the place where, let's imagine that I'm going to represent v of tx by a big neural network. Okay? So now I'm going to replace v of tx by, some parametric version of that v, and I just used theta, which was a bad idea because I wanted to have theta for my, can I change this one into an eta? I'm sorry. I detest when people do that because then you need to change everything in your note, I know. But let me do that. Okay, so that now I can use theta. So this is just a big neural network or a deep neural network. If you have theta represent all the parameters in the network. Okay? And what I want to do is I want to optimize this guy. Right? So if I want to optimize this guy, right, I can view this thing here now as being some loss in theta. Right, theta here, is in some either finite set or Hilbert space, right? And I want to optimize this loss. And so what would you do? Well, you're going to construct, say, a sequence where you're going to say theta k plus 1 is equal to theta k minus d theta, my loss of theta k. Yes?
But what does the VT represent here for the deep neural network? Is it the value of the function of the net? Or
Yeah, that's right. So so this is a function, v here, right? V is a function that go from 0, 1 cross let's say TD or omega, right? And takes value in RD. It's a vector field, right? And I'm just going to parameterize this whole vector field. We know, in fact, that you don't need to parameterize vector field. You could take it as a gradient and parameterize the potential that's associated. People doing score-based diffusion model, if I have time, I'll get to that, are doing this. This is what they do. This is, you will see that this is what they call the score. It's related to what they call the score. And the way they learn the score is that they just parameterize this score, which is this big function, right, on omega n. This is time, this is space. And they just parameterize all that by a neural network, typically a U-net, and then they optimize. So, and they explain to you how you can optimize in this context, right? So this is, a step of gradient descent. I'll make it stochastic in a minute. So if you want to compute this gradient, right? Well, you need to actually do the following thing, which is that given your current theta, so I'll put them here, right? Given your current theta k, you need to solve this equation forward at theta k. You need to solve this one backward at theta k. So every time there is a v, you need to take it at theta k, right? That gives you the value of the x and the eta that you needed here, okay? And then you go back to the objective function, and you say there is a theta here and there is a theta there, and you just calculate the gradient with respect to theta explicitly by taking d over t theta of v. That's the way it's done. So this, and that you do simply by, back propagating through the network. Is it?
I'm still kind of confused. Sorry, I kind of lost track what the x bar actually means in this equation?
So
I mean, how would, okay, you have some...
let's before we go into technicality, let's see if conceptually what I'm trying to do is clear. Imagine that I need to do this optimization here, right? I need to do the optimization. Forget about the red for the moment, just the white. I want to minimize this objective function over all v's.
And so uv is given to me by rho v. Okay. And rho star is something I assume I know.
Right, so I mean,
And v I am looking for.
yes.
So right now you have V, but how do you have the X?
Yeah,
Okay. So there's two steps. Let me, I thought that this part, first of all, I can replace, if I have data from the,
No, I meant the capital X, not the small x.
hold on, bear with me. Bear with me for a minute, I'll write to you. So this is here. Let's, this is the empirical version of the loss. If you give yourself a V, okay, and n data points, so I have n data points, these are my n data points here, I equal n to n, that are samples from rho star, right? Then what I can do is, if I want to evaluate this loss for a given V, V is fixed for the moment, I'll optimize over V, but if I want to evaluate that, draw these n guys, which you assume you have at your disposal, calculate the x's with respect to this, compute that.
Calculate meaning...
Integrate that equation.
So you integrated it.
Yes, so I mean, in practice, there's one more step that I'm kind of sweeping under the rug, which is that you need to integrate this equation, which means that this time integral here, you'll have to replace by, some Riemann sum, trapezoidal rule. You can do that to the accuracy you want, right? This you can integrate to the accuracy you want. That's why I'm not discussing that. But you would have to, integrate this equation, use your own favorite ODE solver, and then evaluate this loss. Where for this integral, use your favorite integrator.
And also one more kind of thing, like, isn't the samples from rho star coming from t equals 1, not t equals 0?
That's right. Sorry. You solve it backward in time. Okay? Thank you. That was so you do that, right?
In the Lagrangian form of the red equation, is this what you get when you find the zero of this expression for ddxt? The backward solution to x.
No. So there's two things now. Now, to do it in practice, we do one more thing, which is we say, I'm going to parameterize that, these guys, like that, right? And so now this becomes an Ln of theta. That's my loss. And here, I need to do this. That's no stochastic gradient descent since I'm using finite amount of data. Well, actually, you can do it with mini batch, obviously, if you, right? So that would be stochastic gradient. This is the full batch version if this is all the data that you have. But then what I explained there, and maybe I went into the wrong order, is how do you calculate this? And that's a little bit complicated. Why? Because you need to take variation with respect to theta, but if you vary theta, that means you vary v, and so that means that, well, if you vary theta, you vary x. And this explanation here, which probably I should have skipped, is how you do that by adjoint method, which is if you want to do this optimization in practice, you can calculate this gradient by an adjoint. You realize that, since this depends on theta, let me maybe, right, if since v depends on theta, then implicitly x depends on theta, every one of them. So I could take a d over d theta of this guy, and then I would have the explicit d over d theta there, and then a d over d theta of this, right? And what I would get, I could, in principle, write down an equation for this object, the dxti for every data point, d theta, this big matrix, right? Because I could, there's a d over dt of this guy. Just to, implicit differentiation chain rule, you will get an equation. This is a monster because the data is in a big space, your parameter is in a big space. You don't want to do it this way. So to not do it this way, the way you do is that you impose this constraint by a Lagrange multiplier, and then instead of having to solve this monster, you just need to make one pass backward in time with x and one pass forward in time with the adjoint, and you have your gradient. That is fairly, I mean, that step is fairly standard.
Okay, so
No.
this really helped. Now I
Okay.
feel like I understand what the x is, but now this is the empirical version, and here we have the densities.
It's the same. I mean, what I've done, you know, in the Lagrange multiplier here, do the empirical version. So you need to impose this, instead of having, this was a constraint that was for every x that has mass, which is all of them, right? I just put that guy for convenience. Then here, of course, you only need to impose this constraint from the x in your data set, right? So you would replace this expectation here, again, by an empirical sum. And so you would have an equation here and an adjoint.
And adjoint, but
This is
just one equation? Or
It's just one equation because this is the ODE for the adjoint and this is the initial condition. You always solve one equation one way and the other equation the other way. Anyone who is not familiar with the adjoint method, I can explain offline how to do that. I understand that there's many steps, but
because
like
I'm still slightly, okay, can do it offline, but can you say now again why the derivative with respect to x bar and not with respect to v? Because you are minimizing with respect to v. I know I already asked that, sorry, but I didn't get
right. So if you do it here, if you stick to this, let me repeat that. If you stick to this version, you'd have to calculate this object. Because when you do variation with respect to v or with theta in v, you also need to calculate what this induces variation with x. So you'd have to do that. That's complicated. So instead of doing that this way, there's a simpler way, which is to say, how do you impose constraints? Forget about infinite dimension optimization. Suppose I want to minimize. How do you do minimization of f of x subject to g of x equals 0? Well, you do minimization of f of x plus lambda g of x, and then you find the lambda so that this g is satisfied.
Yes.
Okay, so the infinite dimensional version of this is this.
Now that I understand why I derivate with respect to the eta, but why with respect to the x bar and not with respect to the v? I mean, here I would still make a derivative with respect to x.
The step that are here, right, are just kind of something which is an internal thing that will at the end allow you to calculate the derivative with respect to theta. That's all it is. Or v. If you want to calculate the derivative with respect to v, the derivative of respect to v is the explicit derivative of this expression with respect to v. Forget about view eta and x bar as being independent of v. And in the gradient that you have estimated, just evaluate x and eta at the solution here. Okay?
So in a sense, we haven't done yet the derivative with respect to
No, and I'm not going to write the derivative with respect to theta. So the derivative with respect to theta is now the one that is explicit on this and whatever comes from there.
And the derivative with respect to x will just be part of it. So
That's
it's
right.
kind of useful to write it.
Yes, yes, yes.
I think I got it.
Okay? Okay. So sorry, so, I mean, I realized, I didn't realize I would get stuck here because I thought that this was more background. But okay, so as I say, I can go over this later. So if we sum up, because I think that my time is almost up, right? At least 15. Okay, so then, so this is a way, a priori, in which, let's try to understand what we have done. If we were to, you're going to do the minimization. So if you do it at empirical level, of course, right, you would need to do that over a minimization over theta in some space, which is equivalent to say that you take, there's some regularization that you need to put over the v, as always, right? But so you would do this minimization, and then imagining that I would have had this minimization is done, what I would have gotten at the end of the day is a velocity field that allows me, if I read it in one way, to push the data which are supposed to be sample from rho star onto sample from rho B. But conversely, I can also draw new sample from rho B and push them onto sample from rho star, new sample from rho star. The quality of these samples, of course, will depend on the statistical, quality that I had here. But this is essentially this generative model that I talked about to do these pictures, these photos. This is what they do. They learn that, and they throw a big U-net to do this. I'll explain to you in a minute how to do the things if I have time. Okay. Now, you see that you can play many, and I'm not going to discuss that because I want to discuss the store-based diffusion. You can play many tricks to make this problem simpler. One of them, as you realize, is that there is this divergence, there is this divergence of V here, a bit annoying. And then here there's an even bigger monster because there's the grain of the divergence of V, right? It's a lot of derivatives, okay? But you can, in practice, what can you do? And again, this is actually done. You can do what's called padding. You pad your problem, which I think for people that, from statistical physics, again, is going to be very, very simple, which is that instead of learning rho star of x and rho b, imagine that I change that into rho star of x, and then I introduce an auxiliary variable, let's call it u. I just do that. I go into the extended space where instead of having just x, now I get into x and u. Okay? And what you do here, the flow that you're going to learn, you take them to be like that. It could be a V, but you could put it to be a potential. You just take this, and you could add this term if you want. Or you may, with the gamma that you could learn, it could be positive or negative. At that level, it doesn't really matter. You could imagine that you eliminate that. Why would you do that? It's because now this is without the gamma, it's the Hamiltonian flow. The Jacobian is 0, is 1. The divergence, is divergence free, right? So you drop all of these terms. Okay? Yeah?
I don't understand naively why is it not divergence free in general, because you don't want it to cross, right?
The divergence is not about crossing. Divergence is about volume.
Yeah.
Right? So, they don't cross, but the volume element here becomes that. That's the Jacobian effect, right? But this, let's eliminate. If you take this guy out, you take gamma equals 0, for example, is divergence free, right? In the padded space, in the extended space, okay? And if you take the gamma, well, the divergence actually simply is a constant because the only thing is, in this case, you just get that the divergence is d times gamma. So very simple. Yes?
Sorry, just to be on the same line, are we already supposed to be understanding how now we are optimizing the V, or you're getting there?
That's the place where there will be ... and I can try to explain that a little bit more next time. But that's, this is the place where you throw your big neural network here and you hope for the best. I'll go in.
I'm happy to throw a big neural network parameter space data,
Yeah.
but I'm not sure I understand the pipeline, what I do with it.
So you take, bear with me for a second. I'll get back to that when I discuss core-based diffusion. Okay, so padding, you can do that. Let me show you another padding, which is that you can, do this. You double the space in that way, and you just simply say this is, what people call nice. You take two velocity fields, say W and V, and you make them evolve like that. This is also divergence free. Because the velocity for x depends only on y, the velocity for y depends only on x. It's divergence free. You can do, this is nice, there's real NVP, you would put something which is like this, and then a B of yt. The divergence of that is also easy to calculate, but let's forget about that. You can just think about that. So you can use padding tricks to actually do this calculation in a way which is easier. Okay, So if I have 10 minutes now, I'm going to explain to you your Lanca's question, how to do that in practice. Okay? Because I think you have put your finger on indeed something which is, so this, right, this way is in fact what people call normalizing flows. Okay? That were introduced quite a while back. And, you know, then I think, you know, I had a paper with Esteban Tabac on that, which predates, in fact, neural network. And then that was taken by people like Danilo Rezende, etc., who actually use these normalizing flows to precisely as generative model, in the way I'm explaining it here. They were very difficult to train in general. And perhaps that's what is that, okay, so what's happening here, right, is that, so first of all, at the beginning, people didn't understand very well how to, they were at the level where you don't use this continuous velocity field, you were trying just to learn a map, which is you take a thing and you move it in one go, the capital T I had at the beginning, right? You wanted really, at the beginning, they really wanted to find a T that would do that. In fact, in the original paper with Esteban, we didn't want to do that. We wanted to do it, but people tried to learn this. That was very difficult because if you want to find a T like that that's invertible, there's a lot of constraints that are not so easy to put on neural network. Okay? So they forgot about this and they say, let's just do, you know, that. Actually, the way. Let's just use flows and try to learn the V rather than the X, but with the same output. But even that.
So they try to learn the X rather than the V?
No, they tried to learn the V. Originally, they were saying, okay, let's just try to learn a map. That's complicated. Then they say, let's try to learn a V, which is such that if I push things through the V, then at time t equal 1, this is, right? But it turns out that this is also quite complicated for a reason which is quite, you know, perhaps is immediate, is that, well, all the steps for the optimization are there, right? You know how to estimate your loss, you know how to calculate the gradient. A priori, you know how to find, you know, a representation by a deep neural network which is expressive enough. But where do you start? Like, you know, how do you initialize this thing? Of course, you could initialize with Vt equals 0. If Vt is equal to 0, that means that originally you just have the identity map, nothing is moving. And then in principle, your gradient should take you towards the actual V. If you try that in practice, it's actually very, very difficult to train because there's very little gradient at the beginning, very little information on where, you know, where the data, what is doing, so what needs to happen, and that didn't work very well. And so the people from, and I'll maybe elaborate on that tomorrow to not do too much today. The people that score-based diffusion model is in fact based on two very simple ideas that but kind of, you know, very very useful. The first one is this, is that what they will do is they will use a stochastic differential equation to turn their data into noise. Okay? So let's write this down. This is not the same X. Allow me to use. I'm going to use this differential equation, which is, say, this one. Let's just look at this. And let's imagine that I solve this equation at time t equals 0 with an X which is a sample from rho star. Okay? So what's gonna, so
What's written here is square root 2 times what?
DWT, it's the stochastic differential equation. Who is not familiar with stochastic differential equation? It's an Orgeneck process. Okay, let me, if you're not familiar with it, let me solve it. This is, the solution is given by this. And this guy here is just in low, this is just a Gaussian process which has 0 mean and variance which is 1 minus, the variance is 1 minus e to the minus 2t times the identity. So, in fact, if you don't know about the SDE, you can just look at this formula, which is, you imagine that what you do in your data, okay, is that you take your data point and you make it fade away exponentially fast and then you add a Gaussian noise to it. Okay? So this guy, as t goes to infinity, will converge to a sample of an n0, just a normalized Gaussian. Right? That's what happened here. Okay? So think about it this way, and you have all seen these images. You can go to the blog, for example, of a song. You have your image, all the pixels. That's x, it's a vector, right? That's your image. And then what you do is that you pass this image by essentially fading it out and adding noise. And what you see is that exactly what I just described, is that the image, your cat, your face, disappears, and then there is like random noise that is replacing it. That's what is done by this operation. Okay? Okay. Now there's another little step that is being made, is that associated with this equation there is a Fokker-Planck equation. And I think physicists that there, which is, so it's not the type of equation that I explained before, because this equation, I'll write it like that. No, I'll write it in a way that you will. There is a drift term, but now there is a diffusion term. Let me first write it like that. For those of that don't know what this differential equation is, it's just the process which is such that its probability density function satisfies this Fokker-Planck equation, or forward-Kolmogorov equation for the mathematician. Okay? And what I'm doing here is I'm assuming that I'm solving this at time t equals 0 by solving it with this initial condition. Right? And now, there's a property of this. The statement that I made here is that it says that rho of t, as t goes to infinity, will actually become, well, just this n0 identity. It will become a Gaussian. And that's what I'm going to declare my base distribution. Right? So you're taking your data and you're putting noise on it. So far, so good. And then what you now realize is that this, and that's something that goes back to score-based diffusion, Vincent, etc., that in fact you can write that as a transport map, because you can rewrite this equation like this. And if I don't have time to finish, I'll do that more tomorrow. A Vt of x times rho t of x. Where what's Vt? Well, it's x minus the gradient of the log of rho t of x. Yes? Because if, the gradient of, so the x rho t give me the x rho t I needed there. And then if I take the gradient of the log, I get the gradient of rho t divided by rho t. There's this rho t that cancel, and so you just get the Laplacian. Everybody sees that this equation is the same as that one. Okay? But now you say, okay, so that means, so let's call this guy, this is what's called the score. Let's give it a name, which is the one that which is st of x. Right? Now imagine that I managed to obtain the score. It's complicated, right? I mean, there's a big cheat here, which is that, of course, this score depends non-linearly on rho t, which depends on the whole evolution. That's complex. But the score that's there, right, if I had it, I had a velocity field here, and now along this velocity field there, provided that this has the right property, I could go backward and forward. Which means that instead of going forward in time where I had my image that becomes noise, I could take noise and go the other way and recreate an image. Okay? And that's precisely what they do. Now, there's a catch with respect to what I have said before, is that now you need to go to t equal infinity, which you can't really do. So you need to go to a finite time, right? But as you can see, everything here fades exponentially, so you hope that the error will not be too big if you take t to be 10, 50 if you wish. Okay? Now the question is, how do you learn the score? Well,
is this Vt the same as Vt was before?
It's another Vt. It's a Vt. This Vt has the property, so it's almost the same as before, except that this Vt has the property that along this Vt, what you have is, you still have that rho t is equal to the push forward. So if I solve, this remains true, but it's written this way now. The push forward of rho star is rho t. So it will go, so it's really what I call the bar, because it goes in that direction. And so it's something that pushes your data at time t equals 0 into, it's actually, is neither. It's going the other way. So it's a push forward. That would mean that if you solve along the flow line there, you're actually going from the data distribution towards rho b. Right? Is that clear or not?
I think you can still do it by characteristics.
Of course. You can do everything that I did before. Simply you need to, so there's, there is one difference. The t equals 0 here has now become rho star with the notation that they've taken there. So you're going to go that way, and then you will have to invert it. And instead of going from 0 to 1, you need to push it further, because at 1, maybe things have not disappeared completely here. Or equivalent, you could put an alpha there and take alpha sufficiently big.
So is it like, how is it related to what you were explaining before? Is it like another case? Or?
So I'll get to that. No. So it's related in the sense that if I were to learn this core and hence the velocity, you can do exactly the same thing as what I did before, which is that you can go forward and backward along this flow to take images of data and push them into noise, and then take noise and push them back into data, which is go from samples from rho star into sample from rho b, and then sample from rho b into sample from rho star. Right?
So, if there was like in a very, very trivial case, like suppose that rho base is n0i, and rho star is n0 sigma. In this case, is there like some very clear?
Yes, I'll get to that. That's going to be my last, and then I'll do it two more. Which is that's actually kind of okay. So I'm going to do two things. You need 2 minutes. 1 minute to explain to you, and then we elaborate tomorrow if you want more detail on this. How do you learn the score? Okay, you can use this objective for every time. So you can do. Let's write down this objective. Let's imagine that I look at this. Clearly, if I minimize this over S, and rho t as st in this case, if I minimize this over S, the minimizer is st is equal to grad log rho. Now expand this guy, and notice that this is, okay, I'll write it like that. Right? This is, sorry, there's a rho t here, and there's a rho t there. I've just expanded the guy above. I expanded the square. Yes? This doesn't depend on S, so I can drop it. And this I can integrate by part, because the grad of the log rho times rho is the grad rho. So I can integrate it by part, and let me write it here so that, the one behind C. What you have is that it's st squared plus twice the divergence of S. So this formula goes back to Vincent, I think. Rho t of x dx. So instead of minimizing the objective function that is there, I can minimize this objective function over S. Yes? But what is nice now is that in the previous case, I had no guess whatsoever about the velocity that I need to learn. But here, by doing this trick, I have created, or we have created, data for every rho t between rho star and the rho b. They are given to you explicitly here. You just take your original data, multiply it by e to the minus t, and add a little bit of noise. So I can sample this guy at any t. Okay? So I can do an empirical estimation of this for any t simply by taking my data, multiplying by e to the minus t, and adding a little bit of noise. And so I can minimize that and find in principle s of t for every t, or globally for all times if you integrate that in time with a weight. If you do that, you learn the score, and now you have the velocity field here. And now you can go back and forth. This turned out to be much, much, much easier as a procedure than the one that I explained before, because in some sense you have a guess for the velocity field, because you have to create, in the other case, I start from rho 0 and I have rho b, and at the beginning I have no connection between the two. I need to find a v that will do the connection. In this procedure, you're explicitly constructing a v that does the connection, then you're learning it. It's much easier. Okay? And now to answer, and I can explain that more that later, but to answer your question, here is a case where you can actually write down what this guy is explicitly. Is take any Gaussian mixture for rho star. You don't need to have a Gaussian and a Gaussian. Take any Gaussian mixture for rho star with an arbitrary number of modes. Okay? Well, if this is a Gaussian mixture, this is a Gaussian mixture. Okay? And you can actually write down an explicit expression for what this is. So if you want to do this procedure for Gaussian mixture, meaning if you want to, your target is a Gaussian mixture of arbitrary complexity, and you want to do this procedure, which is you want to push it into a normal, N01. I can show you what is explicitly the velocity field that will allow you to do that. It's explicit. It's complicated, but it's explicit because it's just, and it's a linear flow essentially. It's not completely for the case of mixture, but so, which is interesting, but we should discuss that maybe later. It's interesting because it might be an avenue, and maybe this is what you are thinking about, to actually try to think a little bit about, the computational complexity associated with all of these problems, which is, when is it reasonable to think that you will be able to learn this score or this velocity field given the complexity of the distribution that are at play, right? Well, here's an example where, in some sense, it gives you a big class where you know that it's learnable with another class because you can write it down explicitly. Okay? I think that's pretty much what I wanted to cover today, so I'll stop here and take a few questions. And
I didn't quite get the optimization over S. How would you, so you sample rho at each time point?
right. So what you would do is not exactly that, is that you would, you can again, if you look at this objective function here, you can integrate it over time, say 0 to t, and then maybe you can put a weight in time, so because not all time should be equivalent. We can discuss that later. So you do that, right? And then you would say, well, again, I'm going to parameterize that by a big, this guy becomes a big neural network, right? And so now, the difference with respect to what we had before is that in the previous formulation, there is a rho 0, rho b, and then there is a rho star, and you start completely in the dark. That's the only two things. You have data from one and then where you want to go, and you need to learn a connection that you don't have, and so you need to make a guess, and your guess will probably be bad, and that's not going to work. Here, you're creating a connection through this diffusion, and then you say, it was a diffusion, but the diffusion is the same as a velocity field, as a transport map. And so they just learned the transport map associated with this diffusion using the data from the diffusion at every time slice. And that is much better. Okay? Now what I'm going to do tomorrow is all of these problems are actually simple. Even, the one before, they are simple because we assume that we have data from the target. When you do statistical physics or Bayesian inference, your problem is more complicated because you want to sample this distribution, but the only thing that you know is like you have an energy function, right? It's like that, and that's it. So you can evaluate this guy pointwise in X. This you don't know, and you'd like to create samples, okay? clearly we can try to do the similar strategy, which is there a way to learn a map that will go from row B to row star, but now by trying to, well, face the fact that we need to have a learning strategy where we need to take expectation with something which is not row star at the beginning because we don't know it. You don't have samples at the beginning. So I'll explain that tomorrow. Okay? But I realize that I put a lot of material and I see, you know, I can also adjust the class. You need to tell that to me afterwards offline, which is I can redo some of these things slower, or I can go into this, or anything that, because I don't want to bombard you with material that at the end of the day you don't understand or it's going too fast. It's much better that I cover less and I then show it to you in more detail than trying to cover all what I had in mind, right? And as I say, if you want to, adjoint method for optimization, these kind of things, if you want to have more detail about it, well, find me at the break and I'll explain to you, why that works and what's the logic behind it. Okay.